Now let's see how we can use information from the first and second derivatives to classify the critical points of a function. So remember that we saw a few lectures back that if you want to know where the local maxes and mins of a function are, that you start by looking for these things we call the critical points, which are the places where f prime is either 0 or undefined. But at the time, we didn't have a really good way of determining whether those critical points were local maxes or mins, or possibly neither. And maybe let me point out something, which is a common misconception people have in thinking about how to classify critical points, where you think, well, why not just plug in those values into f and see what's big and what's small? Doesn't that tell you what the local maxes and mins are? But in fact, it doesn't necessarily. You can have a function like this, where there's a local minimum up here and a local maximum down here. But notice that that local minimum is higher than the local maximum is. So just height information by itself isn't enough to sort of tell you whether a critical point is a local minimum or a local maximum. So what can you do? Well, we're going to learn two different kinds of tests. The first one, appropriately enough, is called the first derivative test. But basically, the first derivative test just amounts to doing this. So let's say you have your critical point x equals c, and you determine that f prime is, let's say it's positive to the left of c and it's negative to the right of c. What we've learned is that when f prime is positive, f is increasing, and when f prime is negative, f is decreasing. And if your graph goes from increasing to decreasing, well, that means that you must have hit a local maximum in between. And in the same way, if f prime goes from decreasing to increasing, well, rather, if f prime goes from negative to positive, then f goes from decreasing to increasing, and so you have a local minimum. But what about the other cases? What if f prime is positive on the left and then also positive on the right? Well, that means that f was increasing, it briefly leveled out, and then it starts increasing again. So your graph looks something kind of like this. And that's not a maximum or a minimum. And something very similar happens if f prime is negative on both sides. Then f is decreasing, level, decreasing. So in both of these cases, this is not a maximum or a minimum. So if you have one of these tables like we were making to find where f is increasing and decreasing, you kind of get for free the location of the local maxes and the local mins of that function. Now, how can you use the second derivative to accomplish something similar? Let's look at the second derivative test. So let's suppose that f prime of c is 0, and that f double prime of c is positive. So what does that mean? Well, f prime of c is 0 means that the derivative is 0, the tangent line is horizontal, briefly. And if f double prime is positive, that means that your curve is concave up. And remember that a concave up curve looks like a parabola, or possibly just half of one. But basically that tells you must be at this point right here, because if you're somewhere on this parabola and you have a derivative of 0, well, the only place that you have a horizontal tangent line here is right here at the bottom. So if f double prime of a critical point is positive, you're sitting at a local minimum. And if f prime is 0 and f double prime is negative, which means that you're concave down, well, that means that your curve looks something like this. And you must be sitting right there. So that gets you a local maximum. Well, there's one last case, which is what happens if the second derivative is 0. Well, it turns out that's actually going to be inconclusive. Right? So what I mean by that specifically is that it could be a minimum or a maximum or possibly neither. Right? This is a little different from the first derivative test. In the first derivative test, we saw a case where you knew that there was not a maximum or a minimum. But with the second derivative test, we don't have a case like that. We just have times when we don't know at all what we get. And let me just convince you of that real quick. So let's consider the following three functions. Say f of x equals x cubed, f of x equals x to the fourth, and f of x equals negative x to the fourth. So for all of these, if you wanted to find their critical points, you'd take their first derivatives. And in all of these cases, those derivatives have only a single critical point, which is at x equals 0. And so what you would do is test that into the second derivative. So the second derivatives look like 6x and 12x squared and negative 12x squared. And notice that in all of these cases, if I plug in 0, well, they all give me 0. Of course, these functions are pretty simple, and we know what they look like. F of x equals x cubed really looks like this, and so that's not a maximum or a minimum at that critical point. F of x equals x to the fourth looks a lot like just sort of a slightly flattened out parabola, so that is a local minimum. And f of x equals negative x to the fourth is sort of a flattened upside down parabola, so there's a local maximum. Right, so just from looking at the graphs, we can see whether you have a maximum or a minimum or neither. But if we're just looking at what happens to f double prime, well, these three graphs with three different behaviors give you the same value for f double prime. They all give you 0. And so that's why this test must be inconclusive in this case, because it can't distinguish between these three cases right here. Okay, well, let's go ahead and work a quick example. So let's find and classify the critical points of the function f of x equal to x to the fourth minus 4x cubed. So we start with the derivative. The derivative is 4x cubed minus 12x squared. Set that to 0 and solve. Both terms have a factor of 4x squared in them. So you factor that out. And so you get two critical points. X is 0 and x is 3. Maybe first let me try the second derivative test. So I take the second derivative, which is now 12x squared minus 24x. We note that f double prime of 0, that was our first critical point, well, that gets you 0. So actually the test is inconclusive. If I plug in 3, we get 12 times 9, which is 108, minus 72. And I don't actually care so much what the exact value is, just that that is positive. Positive means it's concave up, and so I must be looking at a local minimum. Well, this shows you one of the disadvantages of the second derivative test. Sometimes you will get an inconclusive result. So let's go ahead and try the first derivative test. So to do that, we're going to find where f is increasing and decreasing. So these are my two x values. So I want to find where f prime is positive and negative. And so you can pick x values in each of these ranges. So let's say f prime of -1. And it's going to be useful to use just sort of the factored form right here of 4x squared times x minus 3. So plugging -1 into that gets you a positive number times a negative number, so a negative output. F prime of 1 gets you a positive also times a negative. And f prime of, say, 5 gets you a positive times a positive. And so that means your function f is decreasing, it leveled off, decreasing, and then increasing. And so just kind of follow the arrows. We see that right here I have a local minimum, which agrees with what we had found before. And then here at x equals 0, what we have is not a maximum or a minimum. Okay, so once you have this information about the first and second derivatives, you can use that to classify the critical points of a function. And that tells you now where kind of all the interesting things are happening and what the very broad shape is of this function graph.